When you step outside on a clear night and gaze up at the planets visible to the naked eye, Venus shining brilliantly as the evening star Mars glowing red against the darkness, Jupiter blazing, steady and bright. You're seeing familiar neighbours in what seems like our cosy solar neighbourhood. But what if I told you that everything you think you know about our solar system is wrong? That the comfortable image of planets orbiting peacefully around our sun is a dangerous illusion that hides a cosmic shooting gallery, more chaotic, violent and deadly than any science fiction nightmare could imagine. The truth is, our solar system isn't the stable, predictable clockwork mechanism we learned about in elementary school textbooks. It's actually a dynamic battlefield where massive objects hurtle through the void at devastating speeds, where invisible gravitational forces reshape entire worlds on timescales, both geological and immediate, and where cataclysmic collisions capable of ending all civilization happen far more frequently than you might realize. If you're ready to discover the terrifying reality hiding behind our solar system's deceptively peaceful facade, make sure to subscribe and hit that notification bell, because what you're about to learn will forever change how you perceive our cosmic neighborhood. And let me ask you this, if you could witness any single catastrophic event in our solar system's violent 4.5 billion year history, what would you choose to see? Leave your answer in the comments below, and I'll respond to the most thought-provoking and creative responses. Now let's begin to systematically shatter the comfortable myths and misconceptions about our solar system, and reveal the ongoing chaos that literally surrounds us every single moment of every single day. Most people, when they imagine our solar system, picture a serene and orderly collection of planets following neat, predictable circular orbits around our benevolent sun, like some kind of well-behaved cosmic clockwork mechanism, or perhaps an elegant celestial dance choreographed by the laws of physics. But this mental image couldn't possibly be further from the actual reality of our cosmic environment. Our solar system is in truth a dense and deadly minefield, packed with potentially civilization-ending objects hurtling through the darkness at speeds that make high-velocity bullets look like they're standing completely still. The asteroid belt situated between the orbits of Mars and Jupiter alone contains well over 1 million distinct objects larger than 1 kilometer in diameter, and every single one of these rocky bodies represents a potential civilization killer if its orbit were to intersect with Earth's path around the Sun, but that's merely what our current detection systems have been able to identify and catalogue. The true number of dangerous objects in our immediate cosmic neighborhood is almost certainly far higher than we currently comprehend. The Catalina Sky Survey, operating from Mount Lemmon in Arizona, along with the Linear Project, which stands for Lincoln Near-Earth Asteroid Research, have together identified and tracked over 25,000 near-Earth asteroids. These are objects whose orbital paths bring them uncomfortably and dangerously close to our home planet on a regular basis. But even this impressive catalogue of potentially hazardous objects represents only a small fraction of what's actually lurking out there in the darkness. Waiting to be discovered, computer modelling and statistical analysis suggest that there are likely over 25 million near-Earth objects larger than 140 meters in diameter, currently unknown to our detection systems. Objects that are more than capable of causing regional devastation, equivalent to the largest thermonuclear weapons ever detonated by human beings. And that's just considering the objects we think might exist based on mathematical models. The actual number could be significantly higher. To truly understand and appreciate the genuine violence inherent in our solar system, we need to examine the impact craters scattered across planetary surfaces throughout our cosmic neighborhood. These are the permanent scars left behind by cosmic collisions that reveal with startling clarity just how frequently these catastrophic events actually occur. Meteor Crater in northern Arizona, created by an iron meteorite only 50 meters across, demonstrates what even a relatively small cosmic impactor can accomplish when it strikes a planetary surface at typical cosmic velocities, the explosion equivalent to 150 times. The power of the atomic bomb dropped on Hiroshima created a crater nearly 1.5 kilometers wide and over 170 meters deep. This devastating impact occurred only 50,000 years ago, practically yesterday in geological terms, and it was caused by what amounts to a tiny pebble by cosmic standards. The Chicxulub crater buried beneath Mexico's Yucatan Peninsula tells a far more sobering and terrifying story about the scale of cosmic violence. This massive scar in Earth's crust, measuring 180 kilometers in diameter, was created approximately 66 million years ago by an asteroid roughly 10 to 15 kilometers in diameter. The impact released energy equivalent to 100 trillion tons of TNT, or about 2 million times more powerful than the largest nuclear weapon ever detonated. Vaporized rock was blasted into the atmosphere, creating a global cloud that blocked sunlight for months, or possibly years, triggering a global winter that drove the mighty dinosaurs along with roughly 75% of all species on Earth to extinction. But here's what should genuinely terrify anyone who understands the implications. This wasn't some kind of rare cosmic accident or once-in-a-lifetime event. Large impact events happen with disturbing and statistically predictable regularity throughout Earth's history. Geological evidence painstakingly gathered from rock formations, crater studies, and fossil records reveals that Earth suffers major impacts capable of causing global catastrophe roughly every 100 million years, give or take a few tens of millions of years for statistical variation. We are currently approximately 66 million years past the last major planet-killing collision, which means from a purely statistical standpoint, we are mathematically overdue for the next civilization-ending impact event. This isn't fear-mongering or sensationalism, it's cold hard mathematical probability based on 4.5 billion years of documented geological evidence. The Torino scale developed by MIT professor Richard Binzel provides a standardized method for ranking asteroid impact threats on a scale from 0 to 10, with 0 representing no hazard and 10 representing certain global catastrophe. Anything rated above level 4 indicates the potential for regional destruction capable of killing millions of people. Yet despite the existential importance of this classification system, most members of the general public have never even heard of the Torino scale, let alone understand what the various threat levels actually mean. Several objects currently being tracked by astronomers rank above 0 on this scale, meaning they pose measurable, statistically significant impact risks within the next several decades. Asteroid 99,942 Apophis, named quite appropriately after the ancient Egyptian serpent god of chaos and destruction, perfectly embodies our solar system's hidden violence and the constant threat it poses to human civilization. This mountain of rock and metal, measuring approximately 340 meters in diameter, will pass closer to Earth in April 2029 than many communication satellites currently orbiting our planet, traveling at a distance of just 31,000 kilometers above Earth's surface. That's closer than the width of the Pacific Ocean when viewed from space, and significantly closer than the Moon, which orbits at an average distance of 384,000 kilometers. Initial orbital calculations performed when Apophis was first discovered suggested a small but measurable possibility of actual impact, causing widespread panic among the astronomical community, who suddenly realized they had discovered a potential civilization killer with less than 25 years of advance warning. While more precise observations and refined orbital calculations have now ruled out any possibility of impact during the 2029 close approach, Apophis will continue to return repeatedly over the coming centuries and decades, and each successive close encounter with Earth's gravitational field will subtly alter the asteroid's orbital trajectory, making long-term predictions increasingly uncertain and unreliable. There remains a small but non-zero probability that future orbital perturbations could place Apophis on a collision course with Earth at some point in the next few hundred years. But asteroids and comets from the outer reaches of our solar system represent just the beginning of the cosmic violence that surrounds us. Every moment look up at Jupiter, that bright steady beacon in the night sky that many astronomers like to call Earth's protector, and you're actually observing one of the most violent and dynamic places in our entire solar system. Jupiter's Great Red Spot, that famous storm feature visible through even modest telescopes, is actually a hurricane larger than 3 complete Earth-sized planets that has been raging continuously with undiminished fury for over 400 years, with sustained wind speeds exceeding 400 kilometers per hour. Atmospheric pressure at Jupiter's core reaches 100 million times the surface pressure here on Earth, enough crushing force to compress any known material into exotic forms of matter that don't exist naturally anywhere on our home planet. The Galileo atmospheric probe, specifically designed and built to study Jupiter's atmosphere, was utterly destroyed by these crushing forces within just a few hours of entering the planet's outer atmospheric layers. But Jupiter's violence and destructive power extend far beyond its own atmospheric boundaries. The planet's 79 currently known moons exist in what can only be described as a gravitational torture chamber, where immense tidal forces continuously stretch and squeeze these unfortunate worlds with literally unimaginable violence. Io, Jupiter's innermost large moon, experiences tidal flexing so incredibly intense that it powers over 400 simultaneously active volcanoes, some of which shoot fountains of molten lava 500 kilometers high into the airless void of space. Europa's subsurface ocean exists as a liquid only because Jupiter's relentless gravitational torture generates enough internal heat through tidal friction to keep vast quantities of water in liquid form beneath a global shell of ice that continuously cracks and refreezes, creating a surface that looks remarkably like a sheet of broken glass. The Shoemaker-Levy 9 comet impact event in July 1994 gave humanity a terrifying preview of Jupiter's dual role as both cosmic protector and destroyer when this fragmented comet, consisting of over 20 separate pieces, slammed into Jupiter's dense atmosphere. At tremendous velocity, the resulting explosions were visible from Earth, using backyard telescopes creating multiple fireballs, each one larger than our entire home planet. Each individual impact released energy equivalent to 600 times the explosive power of the entire global nuclear arsenal. Combined, the dark scars left behind by these impacts remained clearly visible on Jupiter's surface for many months afterward, serving as a stark reminder that while Jupiter's powerful gravitational field does indeed shield the inner solar system from some incoming threats, it also demonstrates with shocking clarity the absolutely devastating power of cosmic collisions. Saturn, with its breathtakingly beautiful system of rings, might appear more serene and peaceful from our distant vantage point, but these gorgeous rings actually tell a story of cosmic violence that's truly breathtaking in its scale, and implications. Those elegant bands of ice and rock particles gracefully orbiting Saturn aren't primordial decorations left over from the planet's formation. Billions of years ago, they are instead the violently shattered remains of former moons that were literally torn apart by Saturn's overwhelming tidal forces when they ventured too close to the planet. The Cassini spacecraft, during its 13-year mission of studying the Saturnian system, revealed that Saturn's rings are actively and continuously fed by the ongoing destruction of small moons and moonlets that make the fatal mistake of crossing too close to the planet. The Roche limit, named after French astronomer Édouard Roche, represents the critical distance at which a planet's tidal forces overcome the gravitational binding energy that holds a moon together. Any natural satellite unlucky enough to cross this invisible boundary faces an immediate and unavoidable death sentence as tidal forces literally rip it apart, piece by piece. Saturn's moon Enceladus. Despite being much further from the planet than the Roche limit, still experiences enough tidal heating to shoot dramatic geysers of water ice hundreds of kilometers into space through massive parallel cracks in its frozen surface called tiger stripes. These aren't gentle, peaceful fountains, but violent, explosive eruptions powered by the same fundamental tidal forces that tear entire worlds apart. The water and ice from these continuous eruptions feeds Saturn's E-ring, creating a visible trail of destruction that extends completely around the planet. Titan, Saturn's largest moon and the second largest natural satellite in our entire solar system, experiences methane weather patterns and atmospheric dynamics that would make Earth's most powerful hurricanes look like gentle spring breezes. Methane rain falls from towering clouds of complex organic compounds, creating vast lakes and rivers of liquid hydrocarbons, while massive dust storms composed of organic particles rage across continent-sized regions for weeks at a time. The Huygens probe, which successfully landed on Titan's surface in January 2005, detected wind speeds and atmospheric dynamics that revealed a world in constant meteorological chaos, where the weather systems operate with violence and intensity that dwarfs anything we experience on Earth. Mars. The red planet that captures human imagination and represents humanity's next destination for robotic and eventually human exploration, is actually a graveyard that bears witness to some of the most extreme cosmic violence in our solar system's history. The planet's two tiny, irregularly shaped moons. Phobos and Deimos are almost certainly captured asteroids, chunks of rock and metal that were gravitationally snatched from the main asteroid belt and forced into orbit around Mars Phobos. The larger and inner of the two moons' orbits, so incredibly close to Mars that the planet's tidal forces are gradually but inevitably tearing it apart within approximately 50 million years. Phobos will either crash directly into Mars, creating an impact crater thousands of kilometers wide, or be completely shredded into fragments that will form a temporary ring system around the planet. Mars itself bears countless scars from unimaginable violence throughout its geological history. The massive Borealis Basin, covering approximately 40% of the planet's entire northern hemisphere, is most likely the result of a catastrophic impact by an object roughly the size of Pluto during Mars' early formation period. This collision was so unimaginably violent that it stripped away the majority of Mars' original atmosphere and may have completely shut down the planet's original global magnetic field, leaving the surface permanently exposed to deadly solar and cosmic radiation. The energy released by this impact was equivalent to millions of years of our Sun's total energy output concentrated into just a few hours of cosmic destruction. The spectacular Valles Marineris Canyon system, stretching over 4,000 kilometers across Mars' equatorial region and reaching depths of 7 kilometers, represents clear evidence of massive crustal fracturing, possibly caused by the same apocalyptic impact event that created the northern Borealis Basin. This isn't the result of gradual erosion or slow geological processes operating over millions of years, but rather evidence of sudden catastrophic crustal failure caused by violence on a scale that defies human comprehension. The shockwaves from the impact that created these features would have circled the planet multiple times and been felt as devastating earthquakes for months or years after the initial collision. But the violence permeating our solar system isn't limited to planets, moons, and asteroids. Our Sun itself, the life-giving star that makes Earth's biosphere possible, is actually a barely controlled thermonuclear explosion that could potentially end all life on our planet with very little advance warning. Solar flares, which are magnetic eruptions from the Sun's surface, can release energy equivalent to billions of nuclear weapons detonating simultaneously in a matter of seconds. The largest solar flare in recorded history, known as the Carrington event, occurred in September 1859 and was so incredibly powerful that it caused telegraph lines across North America and Europe to spark catch fire and deliver electric shocks to operators. Aurora displays normally confined to polar regions were visible as far south as the Caribbean and Hawaii. If a similar solar event occurred today in our electronically dependent civilization, the consequences would be absolutely catastrophic. Satellites would be permanently damaged or destroyed. Power grids across entire continents would collapse. Communication systems would fail completely, and the resulting social and economic chaos could potentially kill more people than any asteroid impact in recorded history. Our modern technological infrastructure is far more vulnerable to electromagnetic pulse effects than most people realize. A single large coronal mass ejection could send human civilization back to pre-industrial technology levels practically overnight. Coronal mass ejections, or CMES, represent an even greater long-term threat to planetary habitability. These are massive expulsions of the Sun's outer atmosphere that hurtle through interplanetary space at speeds of millions of kilometers per hour, carrying with them magnetic fields strong enough to strip away planetary atmospheres entirely. Mars most likely lost the majority of its original atmosphere to ancient solar storms during a period when the planet's protective magnetic field was weakening and could no longer provide adequate shielding. Earth's magnetic field currently protects us from the worst effects of solar violence, but this protection isn't permanent or impenetrable. The strength of Earth's magnetic field has been measurably declining for the past 2,000 years, and many scientists are concerned that we might be approaching a complete magnetic pole reversal. During such magnetic reversals, which have occurred hundreds of times throughout Earth's geological history, the protective magnetic field weakens dramatically to as little as 10% of normal strength, leaving our planet's atmosphere and surface exposed to the full fury of solar radiation and cosmic particle bombardment. Such exposure could severely damage Earth's protective ozone layer, increase harmful mutation rates in living organisms, and potentially make large portions of our planet temporarily uninhabitable. Venus. Our nearest planetary neighbour provides a stark and terrifying example of what sustained solar violence can accomplish when a planet's protective mechanisms fail this hellish world, with surface temperatures hot enough to melt lead and atmospheric pressure 90 times greater than Earth's wasn't always the acid-soaked nightmare we observe today. Early in Venus history, the planet might have possessed substantial oceans and maintained a relatively temperate climate similar to early Earth, but proximity to our increasingly luminous Sun, combined with massive volcanic outgassing, gradually created a runaway greenhouse effect that boiled away any surface water and created the inferno we see today. The continuous solar wind interacting with Venus' thick carbon dioxide atmosphere has systematically stripped away hydrogen atoms over billions of years, leaving behind a world where it literally rains concentrated sulfuric acid and surface rocks glow cherry red from the intense heat and crushing atmospheric pressure. The transformation of Venus from a potentially habitable world to its current hellish state serves as a sobering reminder of how quickly planetary environments can change when exposed to sustained solar violence over geological time periods. Mercury, the smallest planet and the one closest to our Sun, experiences temperature variations so extreme they would instantly kill any known form of life. Surface temperatures swing from 427 degrees Celsius during the planet's 88 Earth day, long solar day, to minus 173 degrees Celsius during its equally long night. These incredible temperature variations cause Mercury's thin, rocky crust to expand and contract continuously, creating massive cliff systems called scarps that extend for hundreds of kilometers across the planet's surface. Mercury's highly elliptical orbit and unusual rotational resonance create the bizarre situation where the Sun appears to move backwards across the sky during certain parts of the planet's year, creating a landscape of perpetual temperature extremes that would challenge any conceivable technology. But perhaps the most genuinely terrifying aspect of our solar system's inherent violence is how little advance warning we would actually have of approaching catastrophe. The dinosaur-killing Chicxulub asteroid wasn't detected by any early warning system. It wasn't tracked by astronomers or predicted by computer models. It simply appeared in Earth's atmosphere, travelling at 20 kilometers per second, and changed the course of evolutionary history. In a matter of minutes, we have only been seriously and systematically searching for potentially hazardous near-Earth asteroids since the early 1990s, and our detection capabilities, while improving dramatically with each passing year, still contain massive and dangerous blind spots. Objects approaching Earth from the general direction of the Sun remain virtually invisible to ground-based telescopes since they're lost in the solar glare during daylight hours and only visible for brief periods at dawn or dusk, when atmospheric interference makes detection extremely difficult. The Russian meteor that exploded over Chelyabinsk in February 2013, injuring over 1,600 people and causing millions of dollars in property damage, wasn't detected by any of our sophisticated early warning systems until it was already burning through Earth's atmosphere, despite being approximately 20 meters in diameter and releasing energy equivalent to 30 atomic bombs. This relatively small object created a sonic boom that shattered windows across 6 major cities and reminded the entire world just how vulnerable we remain to cosmic impacts we literally cannot see coming. The current generation of asteroid detection and tracking programs, including NASA's recently established Planetary Defense Coordination Office, might sound reassuring to the general public, but the sobering reality is that we have successfully identified and catalogued less than half of the potentially hazardous asteroids larger than 140 meters in diameter, and virtually none of the smaller but still regionally dangerous objects that could cause devastation equivalent to major nuclear weapons. The proposed Near-Earth Object Surveyor mission, designed to dramatically improve our detection capabilities, won't launch until 2028 at the earliest, and will require several additional years to complete even a basic comprehensive survey of near-Earth space. During the years and decades it will take to complete this survey, dozens of currently unknown objects will make close approaches to Earth, and some percentage of these will inevitably be travelling on actual collision courses with our planet. We're essentially driving blind through a cosmic minefield, hoping that we'll see any approaching threats in time to do something meaningful about them. But asteroids originating from the main belt between Mars and Jupiter aren't our only concern, or even our most dangerous threat. Long-period comets originating from the distant Oort cloud, a roughly spherical shell of icy objects surrounding our solar system at distances up to 100,000 astronomical units, can take millions of years to complete a single orbit around the Sun. These ancient icy visitors can be gravitationally nudged toward the inner solar system by close encounters with passing stars, or by the subtle gravitational influence of massive molecular clouds that our solar system encounters during its journey around the galactic center. Long-period comets can give us as little as a few months of advance warning before reaching Earth's orbital distance around the Sun, making any kind of meaningful planetary defense response essentially impossible with current technology. Comet Hale-Bopp, which was visible to the naked eye throughout 1997, measured over 60 kilometers in diameter, large enough to cause a global mass extinction event if it had been travelling on a collision trajectory with Earth. We had approximately 2 years of advance warning from the time of Hale-Bopp discovery until its closest approach to Earth, nowhere near enough time to mount any kind of meaningful defense using current or even theoretically possible future technology. The comet's enormous size combined with its tremendous velocity would have made deflection or destruction completely impossible, even with the combined nuclear arsenals of every nation on Earth working in perfect coordination. Even more disturbing from a planetary defense standpoint is the theoretical possibility of rogue planets' massive stellar objects that have been ejected from their original star systems, and now wander freely through interstellar space. These planetary mass objects, ranging in size from Earth, like worlds, to gas giants larger than Jupiter, are essentially invisible until they're already within our solar system, since they emit no light of their own and reflect virtually no starlight due to their tremendous distance from any illuminating star. The gravitational influence of a rogue planet passing through the outer regions of our solar system could completely disrupt the carefully balanced orbital mechanics that have kept our planetary system stable for billions of years. Such a gravitational intrusion could potentially send Earth spiraling inward toward the Sun, or outward into the frozen darkness of interstellar space. Either scenario would obviously end all life on our planet within a relatively short time period. Recent theoretical studies suggest that rogue planets might actually outnumber ordinary planets, orbiting stars, making chance encounters with these invisible wanderers a statistically significant threat over cosmic timescales. Recent astronomical discoveries like Oumuamua, the first confirmed interstellar object to pass through our solar system, have demonstrated that the space between stars isn't empty but filled with potentially dangerous visitors travelling at tremendous velocities. We had absolutely no advance warning of Oumuamua approach, and by the time our telescopes detected this strange elongated object, it was already leaving our solar system, moving far too fast for any existing spacecraft to intercept and conduct detailed scientific studies. Borisov, another confirmed interstellar visitor, discovered in August 2019, gave a slightly more advanced warning, but still demonstrated just how unprepared humanity remains for objects arriving from outside our solar system. These interstellar visitors could potentially include not just natural objects like asteroids and comets, but also artificial structures created by other civilizations. Though no confirmed examples of such objects have been detected, the point remains that we have no comprehensive early warning system for objects entering our solar system from interstellar space. The violence inherent in our solar system extends to processes happening right now beneath our feet. As you read these words, Earth's protective magnetic field, which shields us from deadly solar radiation, is generated by the complex motion of molten iron in our planet's outer core. But this system is far from stable or predictable. The magnetic field has completely reversed its polarity hundreds of times throughout Earth's geological history, and multiple lines of evidence suggest that we may be approaching another such reversal in the relatively near future. During magnetic field reversals, which can take anywhere from hundreds to thousands of years to complete, the field strength drops to as low as 10% of normal levels, leaving Earth's atmosphere and surface exposed to cosmic radiation and high-energy particles from solar wind. Such sustained exposure could cause severe damage to the protective ozone layer, dramatically increase harmful mutation rates in living organisms, and potentially make large portions of Earth's surface temporarily uninhabitable for complex life forms. The last major magnetic reversal occurred approximately 180,000 years ago, meaning we are statistically overdue for another complete magnetic field flip. Plate tectonics, the fundamental geological process that recycles Earth's crust and helps maintain our planet's long-term habitability, is itself a form of controlled violence operating on geological timescales. Continental plates moving at rates measured in centimeters per year build up enormous stress over periods of thousands or millions of years before suddenly releasing this accumulated energy in earthquakes that can kill hundreds of thousands of people within minutes. The 2004 Indian Ocean earthquake displaced so much solid rock that it actually altered Earth's rotation rate, shortening the length of each day by 2.68 microseconds. Supervolcanoes represent another category of terrestrial violence that could potentially end human civilization with relatively little advance warning. The Yellowstone caldera in the northwestern United States sits directly above a massive underground magma chamber that has erupted with devastating consequences. approximately every 600,000 to 800,000 years throughout its geological history. The most recent supereruption occurred roughly 640,000 years ago, meaning we are rapidly approaching the statistical window for another catastrophic eruption that could blanket most of North America in volcanic ash and trigger global climate changes severe enough to cause mass starvation worldwide. Even volcanic eruptions that scientists classify as moderate by geological standards can have profound global consequences. The 1815 eruption of Mount Tambora in Indonesia caused what became known as the Year Without a Summer in 1816, leading to widespread crop failures and famine across the entire northern hemisphere. A full-scale Yellowstone super-eruption would be literally hundreds of times more powerful than Tambora, potentially ending modern technological civilization through a devastating combination of direct destruction, widespread climate change, and the complete breakdown of global food production systems. Recent computer modeling studies of generation ships and long-duration space missions conducted by researchers like Dr. Frederick Marian at the University of Strasbourg have used sophisticated Monte Carlo simulations to model population dynamics, genetic diversity, and social stability over periods of centuries. Their findings are deeply sobering, even under the most optimistic assumptions. Genetic diversity inevitably degrades. Social and political systems tend toward collapse, and critical technical knowledge is gradually lost over time. Their mathematical models only extended across periods of a few centuries. But the millions of years that would be required for any kind of meaningful intergalactic travel would amplify every single problem they identified exponentially. The minimum viable population required to maintain genetic diversity and avoid the harmful effects of inbreeding over extended periods is conservatively estimated to be between 5,000 and 10,000 individuals, but maintaining such a large population for millions of years in the completely closed environment of a generation ship would create impossible resource management challenges. Every single person requires continuous supplies of food, water-breathable air, and living space. Every person produces waste products that must be processed, recycled, or stored, and every person represents a potential source of conflict, disease, or system failure that could cascade into catastrophic mission failure. But let's zoom out from these terrestrial concerns and consider violence operating on even larger astronomical scales. Our entire solar system, including the Sun and all its orbiting planets, orbits around the center of our Milky Way galaxy at a tremendous velocity of approximately 230 kilometers per second, taking roughly 225 million years to complete what astronomers call one galactic year. During this epic journey, our solar system periodically passes through the galactic plane, where cosmic ray radiation levels are significantly more intense than average, potentially triggering mass extinction events on Earth with a rough periodicity of 26 to 30 million years. Detailed analysis of fossil records compiled over decades of paleontological research suggests that major extinction events do indeed occur with approximately this same periodicity, strongly supporting the hypothesis that our solar system's galactic orbit regularly exposes Earth to periodic increases in cosmic violence that can devastate global ecosystems. The solar system also encounters massive interstellar molecular clouds during its journey around the galaxy. These enormous structures can extend across dozens of light years and contain enough gravitational influence to compress the outer regions of our solar system, potentially destabilizing the distant Oort cloud and sending massive showers of comets toward the inner planets where Earth orbits. Our solar system is currently traveling through what astronomers call the local interstellar cloud, a region of slightly higher density, gas and dust that affects the heliosphere, our Sun's protective magnetic bubble that partially shields us from galactic cosmic radiation. As we continue moving deeper into this cloud over the next several thousand years, Earth could potentially be exposed to significantly higher levels of cosmic radiation that might affect both global climate patterns and the genetic stability of life on our planet. Even more dramatically, our solar system periodically passes relatively close to other star systems during its orbital journey around the galactic center. These stellar encounters occur roughly every few million years and can gravitationally perturb the distant Oort cloud, sending thousands or millions of comets careening toward the inner solar system. The red dwarf star Gliese. 710 is currently heading almost directly toward our solar system and will pass within approximately 1 light-year of the Sun in roughly 1.3 million years, close enough to significantly disrupt the Oort cloud and potentially trigger a comet shower that could continue for millions of years. Nearby supernova explosions represent yet another category of existential threat that could potentially sterilize Earth's biosphere. A supernova occurring within 50 light-years of our solar system could strip away Earth's protective ozone layer, expose the planet's surface to deadly ultraviolet radiation levels, and trigger mass extinction events comparable to the worst in our planet's geological history. There are several candidate stars within this critical danger zone, including the massive red supergiant Betelgeuse, which shows clear signs of instability and could potentially explode at any time, ranging from tomorrow to 100,000 years from now. Perhaps the most psychologically unsettling aspect of solar system violence is how it scales with time over periods of millions and billions of years. The gravitational interactions between planets cause their orbits to slowly but inexorably evolve in ways that are fundamentally chaotic and unpredictable. Computer simulations of our solar system's long-term orbital evolution consistently show that planetary orbits become chaotic on timescales of tens of millions of years. Mercury's orbit is particularly unstable due to relativistic effects, and there is roughly a 1% chance of a collision probability that Mercury could either be ejected completely from the solar system or collide catastrophically with Venus within the next 5 billion years. Such orbital instabilities could potentially trigger a cascade of gravitational interactions that would completely reshape the architecture of our entire solar system, possibly sending Earth into an orbit that renders it permanently uninhabitable, either by moving it too close to the Sun, where surface temperatures would boil away our oceans, or too far away, where the planet would freeze into a lifeless ice ball. The Moon, which we depend upon for tidal stability and long-term climate regulation, is gradually moving away from Earth at a measurable rate of 3.8 centimeters per year. As our Moon slowly recedes over millions of years, Earth's rotation will continue to slow down, and our planet's axial tilt will become increasingly less stable, potentially causing dramatic climate changes that could make large portions of Earth uninhabitable in approximately 2 billion years. The Moon will have moved so far away from Earth that it will no longer provide adequate stabilization for our planet's axial tilt, potentially causing Earth to tumble chaotically through space, with absolutely devastating consequences for global climate patterns and long-term habitability. Looking even further into the deep future, our Sun is gradually but measurably brightening as it ages and exhausts the hydrogen fuel in its core. In roughly 1 billion years, the increased solar radiation will trigger a runaway greenhouse effect on Earth, remarkably similar to what transformed Venus into the hellish world we observe today. Our oceans will boil away into space, and Earth will become completely uninhabitable, billions of years before the Sun actually exhausts its nuclear fuel and begins its final transformation into a red giant star. The violence inherent in stellar evolution will eventually consume not just Earth, but potentially all the inner planets when our Sun enters its red giant phase. In approximately 5 billion years, it will expand to roughly the orbital distance of Mars, potentially engulfing and completely vaporizing Mercury, Venus, and possibly Earth. The outer planets will survive this stellar catastrophe, but will be bathed in intense radiation that strips away their atmospheres and sterilizes any potential life Jupiter's moons, including Europa and Ganymede, which might harbor primitive life forms today, will be completely sterilized by the dying sun's radiation. But let's return our focus to more immediate concerns: the genuine threats we face within human historical timescales rather than geological or astronomical ones. The asteroid impact threat isn't merely theoretical or abstract. We have witnessed smaller versions of these cosmic catastrophes throughout recorded human history. The famous Tunguska event, which occurred in a remote region of Siberia in June 1908, flattened over 2,000 square kilometers of forest, with an explosion equivalent to 15 megatons of TNT. If this same object, estimated to be between 50 and 100 meters in diameter, had struck a populated metropolitan area instead of uninhabited wilderness, it would have killed millions of people and devastated an entire region. The Chelyabinsk meteor event in February 2013, while much smaller than the Tunguska impactor, still injured over 1,600 people and caused widespread property damage across 6 major cities. These documented events serve as stark reminders that Earth truly does exist within a cosmic shooting gallery, where impact events aren't a question of if, but simply when the next one will occur and how much damage it will cause. Current detection and tracking programs have identified several asteroids that will make uncomfortably close approaches to Earth within the next few decades. Asteroid 2022, AP7, discovered quite recently in 2022, measures over 1 kilometer in diameter and follows an orbital path that will eventually bring it relatively close to Earth's orbit, while detailed orbital calculations show that it poses no immediate threat over the next century. Its very existence reminds us how recently we are still discovering potentially hazardous objects that have been sharing our cosmic neighborhood for millions of years, completely unknown to human science. The European Space Agency Hera mission, scheduled to launch in 2024, will conduct detailed studies of the asteroid Didymos and its small moonlet Dimorphos, which was deliberately impacted by NASA DART spacecraft in September 2022. This ambitious international mission represents humanity's first serious attempt to test and develop practical planetary defense technology by demonstrating our ability to deliberately alter an asteroid's orbital trajectory, but our current planetary defense capabilities remain embarrassingly primitive and inadequate. We have no operational systems capable of reliably deflecting or destroying large asteroids approaching Earth. On short notice, the DART mission was essentially a proof of concept experiment conducted against a small, non-threatening asteroid moonlet, with several years of advanced planning and preparation. Successfully deflecting a large asteroid actually approaching Earth on a collision trajectory would require technology we simply don't currently possess, and advanced warning times we are statistically unlikely to have. The so-called nuclear option, involving the detonation of nuclear weapons near an approaching asteroid, has been seriously studied by teams of physicists and engineers, but presents its own significant risks and complications. Fragmenting a large asteroid with nuclear explosions could potentially create multiple smaller impacts spread across a wider geographical area rather than preventing the catastrophe entirely. Timing would be absolutely critical in any nuclear deflection attempt. Detonate the warheads too early in the asteroid's approach, and the fragments might still impact Earth with devastating consequences. Detonate too late, and the explosion might not impart sufficient energy to meaningfully alter the object's trajectory. Space-based telescopes like the proposed Near-Earth Object Surveyor represent our best current hope for early detection of incoming threats, but even perfect detection capabilities wouldn't automatically solve the deflection and mitigation problem. Moving a mountain-sized object traveling at typical cosmic velocities of 20 to 30 kilometers per second requires enormous amounts of precisely applied energy and incredibly accurate timing requirements, neither of which are currently within our technological capabilities. The Planetary Defense Coordination Office, established by NASA in 2016, coordinates international efforts to detect, catalogue, and potentially respond to impact threats. But the office's relatively modest budget and limited resources reflect just how unprepared humanity currently remains for dealing with existential cosmic threats. We collectively spend more money on coffee and entertainment each year than on planetary defense, despite the genuinely existential nature of the asteroid threat. Climate change triggered by cosmic events represents another poorly understood and inadequately studied category of threat that could potentially end human civilization. Large volcanic eruptions like Mount Tambora in 1815 and Krakatoa in 1883 caused measurable global temperature drops and widespread crop failures lasting several years. An asteroid impact could trigger similar or potentially much worse climate effects depending on where exactly it strikes Earth's surface and how large the impacting object happens to be. An asteroid impact in one of Earth's oceans could generate massive tsunamis that would devastate coastal regions worldwide, while simultaneously throwing enormous quantities of water vapor and ocean sediments into the upper atmosphere, potentially triggering global climate changes. A land impact, especially in a region with significant fossil fuel deposits, could throw dust, debris, and toxic compounds into the atmosphere, blocking sunlight and causing global cooling effects. Computer models of large asteroid impacts suggest that objects over 10 kilometers in diameter, similar to the one that ended the age of dinosaurs, could cause global climate changes lasting decades, potentially triggering societal collapse. Even if the immediate impact doesn't directly kill the majority of Earth's human population, the resulting famine, disease, and social conflict could effectively end. Technological civilization solar storms represent a fundamentally different but equally serious category of threat to our increasingly electronic civilization. Our modern technological infrastructure is remarkably vulnerable to electromagnetic pulse effects that could simultaneously destroy power grids, satellite communication networks, and virtually every electronic device that forms the backbone of contemporary society. The Quebec blackout of March 1989, caused by a relatively minor solar storm, left over 6 million people without electrical power for 9 hours, demonstrating our profound vulnerability to space weather events that are actually quite common on astronomical timescales. More powerful solar storms occurring roughly once per century could cause infrastructure damage, requiring years or even decades to fully repair, potentially sending modern technological civilization back to pre-industrial capability levels. Overnight, the economic consequences of such an event would be absolutely catastrophic, affecting every single aspect of modern life, from transportation systems and communication networks to food production, medical care, and financial systems. Space agencies around the world, including NASA, NOAA, and the European Space Agency, continuously monitor solar activity and routinely issue space weather warnings and predictions, but our ability to accurately predict dangerous solar storms remains frustratingly limited. We typically receive only hours, or at most a few days of advance warning before a major coronal mass ejection reaches Earth's magnetosphere, not nearly enough time to adequately protect critical infrastructure from potentially civilization-ending electromagnetic damage. The beautiful auroras that create spectacular light displays at high latitudes during periods of enhanced solar activity are actually visible evidence of high-energy solar particles interacting violently with Earth's protective magnetic field. When these aurora displays become visible at much lower latitudes, as happened during the famous Carrington event of 1859, it indicates that Earth's magnetic defenses are being completely overwhelmed by solar violence of extraordinary intensity. Even more concerning from a long-term perspective is the theoretical possibility of solar superflares, magnetic eruptions from our sun's surface, that could be thousands of times more powerful than the largest solar flares we have directly observed and recorded. Detailed analysis of other stars, very similar to our Sun, has revealed superflare events that would completely and permanently sterilize Earth's surface if they occurred on our own star. While such extreme events appear to be relatively rare based on our limited observational data, the consequences would be so absolutely severe that even a very small statistical probability represents a genuine existential threat to all life on Earth, focusing solely on external cosmic threats. However, misses much of the violence that is inherent in Earth's own geological and atmospheric systems. Our home planet's interior remains largely mysterious to science, but we know with certainty that it contains dynamic processes capable of global devastation. The Siberian Traps volcanic province, which may have directly caused the Permian mass extinction approximately 252 million years ago, released enough molten lava to cover an area the size of Europe to a depth of several kilometers. The associated climate changes triggered by this massive volcanic outpouring killed over 90% of marine species and approximately 70% of terrestrial species, making it by far the most severe mass extinction event in Earth's documented geological history. Similar large igneous provinces have formed repeatedly throughout our planet's history, often coinciding precisely with major mass extinction events. The Deccan Traps volcanic formation in India was actively erupting at exactly the same time as the Chicxulub asteroid impact that ended the age of dinosaurs, suggesting that Earth was simultaneously facing multiple independent catastrophic events during this critical period in evolutionary history. These volcanic mega-eruptions can continue essentially uninterrupted for hundreds of thousands of years, releasing enormous quantities of greenhouse gases, toxic sulfur compounds, and climate-altering aerosols that fundamentally transform Earth's atmospheric chemistry and global climate patterns. The scale of these eruptions dwarfs anything in recorded human history by factors of thousands, making them almost impossible for the human mind to truly comprehend. Earthquake risks extend far beyond the obvious and well-publicized fault lines that most people associate with seismic activity. Major earthquakes can trigger cascading infrastructure failures, leading to secondary disasters that are often far worse than the immediate ground shaking itself. The devastating Tohoku earthquake and tsunami that struck Japan in March 2011 demonstrated with terrifying clarity how seismic events can cause nuclear reactor meltdowns, massive chemical spills, and industrial accidents that compound and amplify the natural catastrophe. Similar cascading failure risks exist worldwide as our technological infrastructure becomes increasingly interconnected and interdependent, making entire civilizations potentially vulnerable to cascade failures that could affect global economic and social systems simultaneously. The New Madrid earthquake sequence that occurred in the central United States during 1811 and 1812 was felt across virtually the entire eastern portion of North America and temporarily reversed the flow direction of the mighty Mississippi River. If similar magnitude earthquakes occurred today in more densely populated regions like California or Japan, the casualties and economic damage could easily exceed any natural disaster in recorded human history, potentially triggering global economic collapse through the disruption of critical manufacturing and trade networks. But perhaps the most philosophically sobering aspect of solar system violence is how it puts human existence and all our achievements into proper cosmic perspective. The Chicxulub asteroid impact that ended the reign of the dinosaurs 66 million years ago was not an unusual or rare cosmic event. Large impacts of similar magnitude have occurred repeatedly throughout Earth's geological history and will continue to occur with statistical regularity far into the future. The mighty dinosaurs dominated Earth's terrestrial ecosystems for over 165 million years, a span of time far longer than mammals have even existed, yet they remained completely vulnerable to cosmic violence that could strike without warning. Modern humans. Homo sapiens have existed for only approximately 300,000 years, which represents less than a cosmic eye blink when viewed against the vast timescales of geological and astronomical processes. We have possessed anything resembling technological civilization for merely a few centuries, and our entire recorded history spans less time than it takes light to travel from the nearest star to our solar system. We have constructed an incredibly complex global civilization that fundamentally depends on stable climate patterns, reliable food production systems, and smoothly functioning technology. But every single one of these basic assumptions could be completely shattered by violent events that are entirely beyond human control, or influence. A single large asteroid impact could instantly end industrial civilization. A major supervolcanic eruption could trigger global famine and societal collapse. A powerful solar superstorm could permanently destroy our electronic infrastructure, returning humanity to pre-industrial technology levels overnight, yet we continue to build and expand our civilization as if these very real threats simply don't exist or couldn't possibly affect us. The psychological challenge of rationally dealing with cosmic-scale threats is immense, and perhaps explains why most people prefer to ignore them. Entirely, human beings evolved sophisticated mental capabilities to respond effectively to immediate physical dangers, like predators, territorial conflicts, and resource competition. But our brains are very poorly equipped to process abstract risks that might occur over geological or astronomical timescales, making it extraordinarily difficult to motivate meaningful action against asteroid impacts, supervolcanic eruptions, or solar storms that might not occur for decades, centuries, or millennia. We are also victims of what psychologists call the availability heuristic, a cognitive bias that causes us to dramatically overestimate the probability of events we can easily remember and visualize, while simultaneously underestimating the likelihood of rare but potentially catastrophic events that don't feature prominently in news coverage or popular entertainment. Most people can recall specific details about terrorist attacks, airplane crashes, or violent crimes because these events receive extensive media coverage and remain vivid in memory. But the vast majority of people have never heard of the Carrington event, the Tunguska impact, the Toba supervolcanic eruption, or dozens of other cosmic catastrophes that have actually occurred within recorded geological history, despite the fact that such cosmic events are statistically far more likely to affect large numbers of people than the more familiar threats that dominate news coverage and public consciousness. The mass media inadvertently contributes to this dangerous misperception by focusing almost exclusively on immediate dramatic events while largely ignoring slower moving or probabilistic threats that unfold over longer time periods. Educational systems also systematically fail to convey the genuine reality of cosmic threats and the violence inherent in our solar system. Most students graduate from high school and even college without understanding basic concepts like asteroid orbital mechanics, solar radiation cycles, magnetic field reversals, or the geological evidence for past mass extinction events. The result is a global population that remains essentially unprepared for the cosmic realities that literally surround us every moment of every day. But developing a deeper understanding of these omnipresent threats also reveals something genuinely remarkable and inspiring about our very existence. Earth has somehow managed to maintain habitually suitable conditions for complex life forms for billions of years, despite being continuously bombarded by asteroids, periodically scorched by intense solar radiation, and repeatedly shaken by massive volcanic eruptions that would seem to make the persistence of life completely impossible. Life on our planet has survived multiple mass extinction events, each one severe enough to eliminate the vast majority of existing species. Yet life has consistently adapted, evolved, and diversified through cosmic catastrophes that would appear to make biological existence utterly hopeless. Our solar system, despite all its inherent violence and chaos, has somehow provided exactly the right combination of conditions, stability and protection necessary for complex multicellular life to develop over geological timescales. Intelligence and consciousness have miraculously emerged from this cosmic violence, giving the universe a means to understand and appreciate itself. We human beings are literally made from chemical elements that were forged in the nuclear furnaces burning at the cores of massive stars and then violently scattered across interstellar space when those stars reached the end of their lives and exploded as supernovae. We carry within our bodies the fundamental violence and creative destruction that formed the cosmos itself. Yet we have somehow learned to love, create art, compose music, appreciate beauty, and contemplate our place in the vast universe that created us. The ongoing violence that surrounds us throughout our solar system makes our existence infinitely more precious rather than less meaningful. Every single moment of peace and tranquility, every beautiful sunset, every shared laugh with loved ones, every scientific discovery that expands human knowledge exists against the cosmic backdrop of forces that could end everything in mere minutes. This fundamental fragility doesn't diminish the meaning and significance of human existence. Instead, it amplifies and intensifies the value of every experience, every relationship, every creative achievement. The same fundamental physical processes that created the breathtaking beauty we observe in Saturn's ring system. The aurora displays that dance across polar skies during geomagnetic storms, and the intricate crystalline structure of individual snowflakes are ultimately rooted in the same cosmic violence that shapes our entire solar environment. Beauty and destruction represent two inseparable faces of the same cosmic processes that govern everything from subatomic particles to galactic superclusters. Our rapidly growing understanding of solar system violence and cosmic threats is also driving humanity toward becoming a genuine spacefaring species, not primarily to escape Earth, which remains our irreplaceable home, but rather to ensure that human consciousness, creativity, and the biological heritage we represent can survive even if our home planet faces a catastrophic cosmic event, spreading human civilization and Earth life across multiple worlds and eventually multiple star systems provides essential backup copies of everything we value most about existence. Establishing permanent self-sustaining colonies on Mars, constructing rotating space habitats at gravitationally stable points throughout the solar system, and perhaps eventually developing the technology necessary to reach nearby star systems represents humanity's most rational response to the cosmic threats we have identified. We may never completely eliminate the dangers that surround us in space, but we can dramatically reduce our collective vulnerability by avoiding the mistake of keeping all our civilizational eggs in one planetary basket. The advanced technology we will need to develop for effective planetary defense asteroid mining operations and interplanetary colonization will also provide enormous benefits for life here on Earth. Better understanding of asteroid compositions and structure could lead to revolutionary new materials and manufacturing techniques. Space-based solar power systems could provide unlimited clean energy, while space-based manufacturing could move polluting heavy industries completely off Earth's surface, protecting our planet's environment. Detailed scientific study of other worlds throughout our solar system helps us understand Earth's climate geology, atmospheric dynamics, and the precise conditions necessary for maintaining long-term habitability. This knowledge proves invaluable as we face both natural cosmic threats and human-caused environmental changes that could potentially destabilize Earth's climate system. The ultimate philosophical lesson of solar system violence is that we exist in a universe far more dangerous, dynamic, and unpredictable than our everyday terrestrial experience would ever suggest. Yet this same violent, chaotic universe has somehow given rise to stars, planets' complex chemistry, and ultimately the emergence of consciousness itself. We represent a temporary arrangement of matter and energy that has somehow acquired the remarkable ability to understand, appreciate, and find meaning in the cosmos that created us. The violence that formed us continues all around us every day, serving as a constant reminder that we are simultaneously fragile and absolutely remarkable survivors in a universe far stranger and more dangerous than human imagination could ever conceive. As we conclude this journey through the hidden violence of our solar system, it's worth reflecting on what this knowledge means for how we live our daily lives and pursue our individual and collective goals the next time you step outside on a clear evening and see Venus shining brilliantly in the western sky. Remember that you are looking at a hellish world where the surface temperature could melt, lead, and it literally rains concentrated sulfuric acid when you spot the reddish glow of Mars. Remember that you are observing a planet scarred by impact craters thousands of kilometers wide that bear witness to collisions violent enough to strip away most of the planet's original atmosphere. When mighty Jupiter rises above the horizon, remember that you are watching a cosmic protector whose powerful gravitational field has spent billions of years deflecting potentially dangerous asteroids and comets away from Earth's orbital path, but also a world of such incredible violence that its atmospheric storms could swallow our entire planet. And when you see our own moon hanging peacefully in the night sky, remember that it was born from violence, a collision so massive it nearly shattered Earth itself, yet ultimately gave us the tidal forces that may have been essential for the development of complex life in our oceans. We live in a solar system of magnificent violence where beauty and destruction dance together in an eternal cosmic ballet that has been performing for over 4 billion years. Our existence is simultaneously threatened and enabled by forces that completely dwarf human comprehension, and this fundamental paradox makes every moment we share together infinitely precious and meaningful. The universe appears to be actively trying to kill us in countless different ways through asteroid impacts, solar storms, volcanic super-eruptions, magnetic field reversals, and countless other cosmic catastrophes. But this same universe has also somehow given us the intelligence, curiosity, and determination to understand these threats and perhaps eventually develop the technology necessary to overcome, or at least mitigate them. That remarkable achievement alone makes us extraordinary survivors in a cosmos far more wonderful and terrifying than we could ever have imagined. Before we developed the scientific tools necessary to perceive cosmic reality, the hidden violence of our solar system represents both our greatest challenge and our most inspiring opportunity to transcend the limitations that have confined life to a single, fragile world orbiting one ordinary star.